In order for some electrical devices to work, we need to plug them into the wall receptacle. In order to work certain limit problems, we need to plug in the value that x is approaching into the function. Hi, my name is Dr. Ron, and welcome to my channel. Before we get plugging away with our limit problems, please click that like button and also subscribe to this channel. Subscribing to the channel and liking the videos helps support my channel so I could supply further content to help you. I'm planning content in other mathematical areas besides calculus, such as algebra and probability and statistics, but also in areas of applied mathematics, such as chemistry and physics. In my previous video, we learned that the first step in approaching a limit problem is to plug in the value that x is approaching. In this case, I've written as a, where a is a real number. We'll plug that into the function itself using our Algebra 1 style substitution, and we'll get a result, L. If L is a real number, that's a sign to stop. We found the answer, we found the limit as x approaches a of our function. A second possibility is L is a non-zero number divided by 0. For example, negative 5.2 divided by 0. In this case, L is undefined. In general, if we get an undefined result, the limit does not exist. It's a DNE. But typically, we want to do one more test called a sign analysis test before we say strictly that this is just undefined. We'll see this in an example in a minute. The third possibility is that we get what is known as an indeterminate form for L. For example, 0 divided by 0, infinity divided by infinity, and there are other indeterminate forms that we'll be examining throughout our calculus studies. If we get an indeterminate form, at least for first year calculus, this is an indication that this limit exists and that what we have to do is more work to actually find that limit. For the sake of review, let's do a problem where L is actually a real number. I'm going to make up a problem. Let's say f of x equals 4x squared minus 2x plus 7. This is a polynomial. In general, polynomials, well, not in general, polynomials simply do not have domain issues. The domain of x for any polynomial is going to be all real numbers. Let's write that. So as a consequence, then, the limit as x approaches, I'm going to randomly pick 2. It's an easy number. Of our function f of x is going to be simply the limit. Notice that I keep writing the limit. As long as I haven't taken the limit yet, I must keep writing this lim x little arrow 2. As a word of caution, if you haven't taken the limit and you stop writing it, you may lose points on an exam. Now we're going to go ahead and take the limit by directly plugging in this number to see what we get. I'm plugging into here. This is just algebra 1. 2 squared is 4. 4 times 4 is 16. Minus 4 plus 7, which is just going to be 16 plus 3, or 19. And so in this instance, the limit as f of x, the limit as x approaches 2 of f of x is indeed 19. You can use either your TI-84 or other graphing calculators or a number of online graphing utilities that are available today to test this. What you would do is go ahead and graph, let's say y equals 4x squared minus 2x plus 7 in one of your graphing utilities, and ask, what number do you approach from the left and the right as x approaches 2? It should be 19. Now let's try a problem where we end up with the value L being an undefined number. For example, let's define our function f of x equaling x plus 5 over x minus 1. And we're interested in the limit as x approaches 1 of this function, f of x, which we will rewrite by substituting the right-hand side expression for f of x, x plus 5, x minus 1. Again, continuing to write the limit as x approaches the value, in this case 1, until we actually take the limit by substituting 1 into our expression. Let's go ahead and do that. So we have x, or 1 plus 5 over 1 minus 1, and we arrive at 6 over 0. This is undefined. But we want to ask another question. What is happening on either side of this vertical asymptote? Recall from pre-calculus that if you can cancel a denominator domain issue using a numerator factor, then the domain issue is a whole, and the limit can certainly exist at a whole. We don't care what happens at the exact value, it's just an approach. On the other hand, if you have a vertical asymptote, as we do in this case, there's nothing we could factor from x plus 5 to cancel x minus 1, or at least not easily. And in fact, I think there isn't anything that you can do that will work. Let's go ahead and do the sign analysis test. Sign analysis. To do this, we're going to draw a number line, and we're going to locate our vertical asymptote, in this case, x equals 1. If it helps you, go ahead and draw on the dotted line that you normally would if you were drawing in a vertical asymptote on an xy plane. And there's our number 1. What we want to do is pick values in either of these two intervals. I have an interval from -infinity to 1, and another interval from the number 1 to +infinity. You can pick any number in this interval. Of course, we want to pick the easiest values we can. In the left-handed interval, 0 is clearly the easiest value to pick. And if we plug in 0 into our function, 0 plus 5 over 0 minus 1, we end up with a -5. And what's important isn't the 5, it's the negative. It's the sign that we're interested in. Likewise, we'll pick an easy number in the right-hand interval. Let's say 2. Plugging in gives us 2 plus 5 divided by 2 minus 1, which is equal to +7. Again, I'm not interested in the 7 part. I'm interested in the sign, or the positive. What this tells us is that if we were to sketch this graph rapidly, again, here's our vertical asymptote at x equals 1. This being equal powers in the numerator and the denominator, we're going to have a horizontal asymptote at the ratio of the coefficients 1 over 1, or also 1. So that's y equals 1. And our graph is going to look something like, let's see, when x is equal to 0, y is going to be -5. So that is going to be our 1, 2, 3, 4, -5 is going to be our y-intercept. And it's going to look something like this. There's going to be an x-intercept, of course, and we're going to have the rest of the graph up here. The important point is that as we approach 1 from the left, in other words, the limit as x approaches 1 from the left of this function, we're going to get negative infinity, and that's where this negative from the sign analysis comes in. Likewise, if I take the limit as x approaches 1 from the right of this function, we get positive infinity. Because they're going in opposite directions, they will never meet up. And in this instance, the function as x approaches 1, or the limit of this function as x approaches 1, is truly a DNE or does not exist. I've modified our original problem slightly by converting the linear denominator into a quadratic denominator by simply squaring the x minus 1 expression. If I take the limit as x approaches 1 of this function now, I'm still going to end up with 6 divided by 0, which is undefined. But this time, when we do the sign analysis test, we notice that the squaring of the denominator keeps everything positive. As a consequence, if we look at what the graph might look like for this particular function now, well, we're still going to have our vertical asymptote at x equals 1. We will now have a horizontal asymptote at y equals 0, or on the x-axis, again, because we're dealing with a linear expression in the numerator over a quadratic in the denominator. And we're going to end up with a function that looks something like this. Again, this is just a quick sketch. It's not a graph. But notice that whether I'm approaching from the left or from the right, in other words, as x approaches, the limit as x approaches 1 from the left or the right of this function, I'm going to get a positive infinity on either side. We can conclude then that the limit as x approaches 1 of this function, in this case, x plus 5 over x minus 1 quantity squared, is going to be positive infinity. Now, strictly speaking, this is still a does not exist because we can never get to infinity. However, we are indicating that in this instance, our limit is heading toward positive infinity. Now let's look at a situation where L is an indeterminate form. For example, 0 over 0. In this case, we're taking the limit as x approaches 7 of x squared minus 49 over x minus 7. If we plug in the value 7 and do the appropriate arithmetic, we arrive at the indeterminate form 0 over 0. What this tells us is that the limit of this particular rational function exists, but we have to simply do more work in order to find that limit. We're going to use some of our techniques from algebra in order to do more work and find this limit. In this instance, we notice that x squared minus 49 is simply a difference of squares. It's x squared minus 7 squared. In our denominator, we still have x minus 7. If I go ahead and factor the numerator, we will arrive at x minus 7 times x plus 7, and still divided by x minus 7. We now see that we can cancel the denominator issue, the domain issue, and we arrive at the limit as x approaches 7 of x plus 7. Taking the limit by plugging in 7 for x, we get 7 plus 7, which is equal to 14. if we were to graph this new result, what we would find, labeling our x, y coordinate system, that we have a line with slope 1 and a y-intercept of +7, which will look something like this. But as we come to the value x equals 7, our line will now have a hole. Remember, just because we canceled the domain issue from the denominator does not mean that we could completely forget the domain restriction in the original definition of our function. But in this instance, since it's no longer a vertical asymptote, but rather a hole, what we see is that as x approaches from the left or the right, either way, we're going to arrive at the same result, y or f of x equals 14. And that is the limit. Again, here's another problem where if we plug in the value, in this case for h, for this particular function, we end up with 0/0 or an indeterminate form. Again, this means we have to do more work to actually find the limit. In this instance, factoring will not help us. But as you recall from some of your pre-calculus problems, we could use the conjugate trick. In other words, if I change the sign here for this numerator from negative in this case to positive, and please note that the sign inside the radical does not change, it remains positive. And if I form the number 1, in other words, the conjugate divided by itself, and multiply that, I could make the offending denominator go away. Here, radical 16 plus h times radical 16 plus h is 16 plus h, and -4 times +4 is -16. The 16s cancel. This leaves me with an h in the numerator and another one in the denominator, and they can also cancel. The result is the limit as h approaches 0 of 1 over this particular part of the conjugate. Taking the limit by plugging in h equals 0 gives me radical 16 plus 4 or 4 plus 4, which is 1/8. And that is indeed the limit for this particular problem. Now we've learned some tricks and techniques from algebra that we can use to solve those limits where we have a 0/0 or an indeterminate form. But sometimes we get an indeterminate form and our algebra techniques no longer work. What do we do now? Well, that's the subject of the next video. I'll see you there. And again, please subscribe to this channel and like this video. I'll see you next time.